Okay, welcome to Lesson 5. We're going to talk about discrete random variables and probability models. So first we're going to talk about what random variables are, make a distinction between discrete and continuous, and then we're going to talk about some characteristics about discrete random variables. So first off, random variables. So it's a quantity that takes on a real number value for every event in the sample space. There's a number of ways we can identify and define a random variable. So each value of the random variable has a probability associated with it, the probability that we observe that value. We typically will use capital letters at the end of the alphabet to describe random variables, although occasionally you see other values as well. But typically it's letters towards the end of the alphabet. So there are going to be two main types of random variables we look at. So discrete is what we look at here in week 1. So here a random variable is going to be discrete if it has a finite countable set of values. So typically these are going to be non-negative integers, 0, 1, 2, 3, 4, and it might have a cap, it might not. Totally depends on how it's defined. But yes, typically it's going to be non-negative integer values. Continuous, that's going to be the case. Maybe you're collecting something quantitative, like a distance, a speed, a weight, a density. So the idea with a continuous random variable is that it can take on any number value within whatever specified interval. So instead of just being 1, 2, 3, it could be 1.5, 3.4, that kind of idea. It can definitely be equal to fraction or decimal values as well, whereas discrete cannot. So I just kind of threw this slide together here. I wanted to talk a little bit about it. So in general, if I am collecting a variable of interest, such as I am going to have categorical or quantitative. We'll go more into this, I believe, in week 3's notes. But so if what I'm collecting is categorical, so suppose I'm looking at eye color, I might go ahead and take a random sample of 20 students and ask them what their eye color is. And there is a set number of categories. They might say, okay, well, brown, blue, green, black, hazel, whatever. There's a set number of categories that will be available. So typically my random variable will be count of a particular category. So in general, you're just going to pick on one category. Maybe I'm interested in the number of people with brown eyes. So I might be looking out of 20. I'm just going to ask 20. So X, my random variable here, I'm going to be looking at the number of people with brown eyes out of 20. I could have values equal to 0, 1, 2, all the way up to 20, right? So I can't have fewer than 0 people with brown eyes. I can have 1, I can have 2, I can have 3, all the way up to 20. But I can't have more than 20 people with brown eyes if I only ask 20 people. So that's the idea. So that would be an example of a discrete random variable. So, and then in week 2, we're going to get into looking at more of quantitative variables of interest. So in general, if I have a quantitative variable of interest, it's going to be a continuous random variable. So I'm going to look at body weight of cats. It's something I vaguely know about, not a lot about, but so I might go ahead and I might collect the weight of, so cat weight, and in pounds, because face it, we don't use the metric system over here. We should, probably. But so if you're dealing with a quantitative variable of interest, so you're collecting body weights of cats, your random variable is just going to be the body weights of cats. It's a little bit different if you have a categorical. You're going to pick one of the categories, and usually it will be count of a category. and that will be a discrete random variable. So it'll be this first scenario when we are collecting something categorical and have a discrete random variable that we discussed this week. So when we have finite probability models, the big thing here is what we want to do is list all of the possible values that the discrete random variable can take, as well as include the probability of observing each of those values. So we want to know what's possible and how often does it happen. So the finite probability model, it's going to list all of the possible values for our random variable x, and then it's going to list the probability for each of those values. So when we do this, when we have it set up, each of those probabilities for all of the values that it could take on have to be between 0 and 1. You can't have probabilities less than 0, and you can't have probabilities more than 1. If you have a probability of 1, it means 100% it's guaranteed to happen. If you have a probability of 0, it means it never happens. It cannot happen, it's impossible. So in general, they're usually going to be between 0 and 1, but they could be equal to 0, they could be equal to 1. When you take all of the possible categories or values that the discrete random variable could be, and you add the probabilities associated with each, you should get 1. So basically, if I say, hey, you know what are the probabilities of all possible things in the sample space happening? It should be 1, 100% guaranteed to happen. And then probabilities are disjoint. So if I were to look at x equals number of brown-eyed people out of 20, I could have 0, 1, 2, ... all the way to 20. The idea of my probabilities being disjoint is if I collect 20 people and observe 0 people with brown eyes, I cannot also observe 2. I can only observe one of these values at a time. So that's what we mean by disjoint, is it can only happen in one category at once. And we will show an example coming up, and I'll go more into checking these properties as we go. Okay, so here's our example here. It's about emails. So there was a big survey. They took a bunch of students and they said, okay, look on your student email account. How many times did you check your email? Which does require us to kind of recall accurately. But how many times did you check your student email in the last 24 hours? So when they asked these students in this survey, they had students that said 0, students that said 1, 2, 3, or 4. They didn't have students that said more, and you can't have students say they checked it, 2.5 times. You can only check it a whole number of times, and you can't check it fewer than 0. So our random variable here is the number of times they checked their email in the last 24 hours. So if I wanted to look at this and go, hey, is this a legitimate probability model? There are a number of things I could look at. If you look at these probabilities here, they are all between 0 and 1, so that's good. Further, if I went ahead and I added those probabilities together, that sum should equal 1. So the probability of all possible responses, if I add the probabilities together, I should get 1. And then further, x is equal to 0, x is equal to 1, x is equal to all the way through 4. These are disjoint values. So if a student said they checked their email exactly 0 times, they could not have been counted in any other category. That's the idea, is they can only be in one category at a time. They were only allowed to answer once. So now that we have this probability model, we can use it to answer questions. So the first one we're going to do is, what is the probability that I go ahead and I randomly select a student from this population that has checked their email exactly 3 times? So what we're asking is the probability that my random variable is exactly equal to 3. So I'm interested in specifically just when it's equal to 3. So that's just going to be equal to 0.25, or 25% of the chance. 25% of the time I randomly select a student from this survey, I could expect to randomly select a student that checked their email exactly 3 times in the last 24 hours. Another question, what is the probability of randomly selecting a student that has checked their email at least 3 times? So at least 3 times indicates 3 or more. So I am now interested in the probability x is equal to or greater than 3. So now that I know that these are disjoint, I can just say, oh, that's equal to the probability x is equal to 3 plus the probability x is equal to 4. And I don't have to subtract the intersection because they're disjoint. So the probability that x is equal to 3 is that 0.25 plus the probability that x is equal to 4 is that 0.23. So I should get 0.48. So that's saying if I were to randomly select a student that took this survey, 48% of them checked their email at least 3 times in the last 24 hours. So we were just using what we call a PMF, or the probability mass function, or we will be. Okay, the CDF is a function for, well, in the discrete case, you sum all of the probabilities up to whatever value you're looking at. So the CDF for, say, if I wanted to look at the student email example, and I wanted to say, like, hey, what's the probability that at least 2 times the students checked their email in the last 24 hours. I want to look at the probability that it's equal to 0, equal to 1, and equal to 2. I want to include anything below that point. So it's specifically equal to that probability that the random variable is less than or equal to, and it is important that or equal to, especially in the discrete case, whatever value that you're interested in. So you're going to start from whatever your smallest value of x is all the way up to this value that you designate here. So for all values of x. Your CDF has to be between 0 and 1. Before any values are observed and the probabilities are 0, your CDF will be 0. But once you have observed all values in your sample space, it'll be equal to 1. It is something that is non-decreasing, for those of you that like to talk about non-decreasing here. So we are still going to grab the email example. So this bottom portion here should look familiar. It's our values for x and then the probabilities associated with them. That is our PMF, our probability mass function. So if I want to say, hey, what is the my P of 2? So this is just probability that x is exactly equal to 2. Well, that is going to be just that 0.26. Versus now if I start talking about this CDF, I'm going to fill in these values first. So my CDF at 0, the only thing I've seen below that is 0, so 0.09. My CDF at 1, I now need to add these two, so 0.09 plus 0.17, so 0.26. My CDF at 2, I now need to add 0.09 plus 0.17 plus 0.26, so I should get 0.52. And then I can keep going for all of these. Strongly recommend checking and doing the math yourself. So like here, I would essentially be adding these 4. So 0.52 plus 0.25, 0.77. And then that last one, add all 5 of those probabilities. It should equal 1. Anytime it does not add to 1, that tends to indicate that, hey, one of your possibilities is missing or something's off. If it's very close to 1, it could be that there was a small rounding issue. You will see that occasionally where it just is just shy of 1 or just over 1. But if it's definitely different than 1, it's a problem if you have added all of your probabilities, and it's very different. So what is my CDF value? So if I wanted to write that in terms of probability, that's the probability that x is less than or equal to 2. So that's the probability that x is equal to 0, plus the probability x is equal to 1, plus the probability x is equal to 2. So we went ahead, we calculated that here. It ended up being 0.52. So your PMF value at 2 is 0.26. That's the probability of observing students with exactly 2 email checks in the last 24 hours. Your CDF at 2 means the probability of observing students with 2 or fewer email checks in the last 24 hours. So that's 52% of those students. So now that we have the PMF and the CDF, what we like to do a lot is we like to talk about expectation as well as variance or standard deviation. So when we talk about expectation, what we're talking about essentially is a weighted average. So if I have a discrete random variable with d possible outcomes, I'm going to go ahead and I'm going to sum over all of the possible outcomes and the probability, like multiplied by the probability of seeing that outcome. And I'm going to add that across all possible values and their probabilities. And what you get, it will be a weighted average. So it is our expected value. And in general, when we say, oh, we expect this, like we tend to be hinting at, on average, we expect to see this. So the expected value should make you think average. So this is the Greek letter mu. That is average. So for the email example, we might want to go ahead and calculate the expected number of times a student checked their email in the last 24 hours based on this PMF. So what this is saying is, hey, given the results from the survey, if you took all of the students, on average, how many times was the email checked in the last 24 hours across all the students? So, I mean, right off the bat, I can tell you it'll be somewhere between 0 and 4. It's not going to be equal to 0 or equal to 4, but so if I want my expected value here, I'm going to take 0 times the probability here, so 0.09. I like to put parentheses around. It helps me not goof up my addition and multiplication, plus 1 times 0.17 plus 2 times 0.026, nope, 0.26 plus 3 times 0.25 plus 4 times 0.23. So essentially what I did is I took the product of 0 and 0.09 plus 1 times 0.17 times 2 plus 0.26 plus 3 times 0.25 plus 4 times 0.23. So I really like the first couple, 0 plus 0.17 plus 0.52 plus 0.75 plus I think 0.92. Let me double check. So yes, and I go ahead, add those together, and I get 2.36. So this is my expected value of x. So what this says is if my random variable that I'm interested in is the number of emails, a number of times the emails were checked in the last 24 hours, on average, for students in this survey, students checked their email an average of 2.36 times in the last 24 hours. And since it is an average, it is okay to leave this as a decimal. If we were saying, hey, how much do we expect this individual to check it, that might be different. But since it's an average, it can be a fraction or a decimal. So expectation should make you think, okay, well, this is an average. So now that we cut the average, we might like to talk about, well, okay, well, how spread out? So from student to student, how far are they varying from that average that we calculated? So we have the variance, which has some really nice statistical properties. It is denoted by the Greek letter sigma, or sigma x squared. So it's a measurement for the variability. So it's not exactly equal to the average distance from the mean for every value, but it's very close to that idea. So if we say something, hey, it varies on average this much, we're talking about, well, specifically we're talking about the standard deviation, but we're looking at how spread out the values are. So you would denote it Vx. Sometimes I see people write var x. Honestly, if you wrote either of those would be perfectly acceptable. So the way we'd calculate it is the expected value of x squared minus the expected value of x squared, and we'll go through that. So note that the expected value of x squared, so it's calculated similarly to when we were calculating the expected value of x, except now instead of the value of x, we're putting x squared. So x squared times the probability of x for all of the values. So in the email case, we go, oh, well, 0 squared times that probability of seeing 0 emails, plus 1 squared times the probability of seeing 1 email, or 1 email check. The standard deviation is highly related. It is the square root of the variance. And a lot of times, for practical reasons, people like to talk about the standard deviation when talking about the spread. People talk about, okay, well, on average, this is, a typical, like how far a value it differs from the average. So on average, how far are the values from the overall average? It'll be this much. Things that are useful about the standard deviation is it does have the same units as the random variable or mu, whereas the variance has the units squared. So in some cases, having the units squared adds this extra complication. So if you square root the variance, it might be easier for people to understand talking about the standard deviation. So to calculate the standard deviation, all you need to do is take that variance you calculated and square root it. Just note that later on, that square rooting has some properties that we don't like as much. So there are some reasons that we do prefer the variance over the standard deviation. But for the most part, if you're working with a client or working in the field, most people will want to talk about the standard deviation. So back to our email example, we want to go ahead based on this PMF. So we're looking at number of times a student checked their email in the last 24 hours and the probabilities associated with each. How many times we want to know what the standard deviation of the number of email checks was for the last 24 hours. So on average, how many times? Okay. Okay, so here we are, back to our example, variance and standard deviation. So we're going to use the email example. So they want to know how much number of times the students check their email deviated from the mean. On average, they're looking at, they specifically want the standard deviation. We'll try and be very clear about what we want. So the first step is you have to calculate V of X, so the variance. Once you calculate the variance, you have that additional step of square rooting it, and you have the standard deviation. But it's much, much easier if you calculate the variance first and then square root. So it's going to be the expected value of x squared minus the expected value of x squared. So we calculated the expected value of x. Expected value of x, that was at 2.36. So like emails, email checks. This part right here though, the expected value of x squared, we still have to calculate. So we are going to go ahead and do that. So the expected value of x squared, it's going to be 0 squared times the probability of seeing 0, so 0.09, plus 1 squared times probability of seeing 1 is 0.17. And we're going to continue through here. So 2 squared times 0.26 plus 3 squared times 0.25 plus 4 squared times 0.23. So I end up getting, I really love the first one. It's just 0, 1 times 0.17, so 0.17, 4 times that's a little over 1, 1.04, is 2.25, plus 3.68. We end up getting 7.14. So note, this was a side quest. We didn't answer what the variance is. We just answered what the expected value of x squared is. So now we have to go back. So my variance is equal to expected value of x squared minus the expected value of x squared. So that 7.14 minus that 2.36 squared. One thing to note is the variance should never be less than 0. It should always be non-negative. It could be equal to 0, and that's the scenario where every single value in the data set is the same exact value. However, it can never be negative. So just a note there. If you do find yourself calculating the variance and you get a negative number, something's gone sideways, that's a good way to remind yourself to, hey, go back and check. Something went wrong in my math here. So I end up getting here 7.14 minus 5.5696. So I end up getting 1.5704. So that's my variance. So now my second step, if I want my standard deviation of x, I need to square root the variance. So I'm just going to take the square root of that 1.5704, and this is not math I can do in my head, so definitely stop, plug this into a calculator or R, and end up getting what, 1.253. So the idea here is the number of times a student checked their email varies on average. So if you see or hear that phrase varies on average, we are specifically talking about the standard deviation. So 1.253 times in the last 24 hours. Oops. So on average, it looks like students check their email 2.36 times on average, and they varied on average from that average of 2.36, about 1.253 times in the last 24 hours. So it is useful, definitely, to talk about both variance and standard deviation. Quite honestly, they're really, really related here. One's just the square root of the other. So if you have a large variance, you're going to have a large standard deviation, vice versa. Just note that a lot of times, like a client will probably want to talk in terms of standard deviation because it will be in the same units, and the variance will be in the units squared. So then we might have ourselves linear combinations. So if you have a random variable x and you have constants, we're going to name them a and b, we can go ahead and say, okay, well, if I want the expected value of this new random variable w, which is a times x plus b, you can go ahead and you can separate the constant out. So the expected value of a constant, it's constant. It always stays the same. It's just going to be that constant. And then the expected value of a constant times x, you can pull that constant out. So you'll get a times the expected value of x plus b. Variances are a little bit different. So when you go ahead and you break up the variance of ax and the variance of b, if you have a constant, it doesn't vary at all. It has no variance. Its variance is 0. So this part, the variance of b goes to 0. And when you take a out, your constant, you must square it. So it is slightly different than when dealing with expected values, just something to note. So if you wanted to find the variance of w, it's going to be that constant that was multiplied by the random variable x. So a squared times sigma squared. So we're going to go through an example here next. Okay, so a bookstore, they go ahead, they buy 3 copies of a book to sell. X is the number of copies that is sold, and W is the net revenue. So it's the idea like they buy it for a price, they sell it for a price, how much money do they make? So it's totally dependent on how many books they sell. So they bought 3 copies of the book. They could sell 0 copies of it. They could sell 1. They could sell 2. They could sell 3. Can't sell more than 3 copies if you only have 3 copies. That's the idea. So we want the expectation and standard deviation of the revenue. Just a moment. Let me see. Okay. I just wanted to see if there was space here. So expectation here. So expected value. I'm going to calculate the expected value of x first, and then find the expected value of w. So they want the expected value of w and the standard deviation of w. So the easiest way to do that, using the rules from that last page, are going to be find the expected value of x, then find the expected value of w, then find the standard deviation of x, then get, well, technically this variance of x, and then the variance of w, and then square root. So my expected value of x, so I'm going to go ahead and I'm going to do that setup. So 0 times 0.1 plus 1 times 0.2 plus 2 times 0.25 plus 3 times 0.45. So let y'all calculate there for a second. I'll double check here. But 0 plus 0.2 plus 0.5 plus, I believe, 1.35 should be about 0.205. So just a note, I found the expected value of x. It's not the same as the expected value of w. So my expected value of w it's going to be the expected value of 12x minus 10. Oops. Just note that I tend to use square parentheses for expected values. It's totally fine if you did rounded. It doesn't make much of a difference. It's more of a habit. Totally depends on who your professors are. So that's just going to be equal to 12 times the expected value of x minus 10. We can go ahead and plug this expected value in, so that's going to be 12 times 2.05 minus 10. Do our math there. What is it? 2460. Let me see. Yeah. Minus 10. I'm going to get a 1460. Note, W is in dollars. So what this means is on average, I expect to make $14.60 net revenue. That's what we're getting at here. So that's my expected value here. I'm not sure we're going to have plentiful room here, but we will try. The next step, if I want the standard deviation, you have to calculate the variance first. So we're going to find the variance of x, then we'll find the variance of w, then we'll square root. You do not want to square root until the end. It will not work very well. So just keep that in mind. So that's the expected value of x squared minus the expected value of x squared. So we have this part right here. We have to calculate the value of expected value of x squared. So expected value of x squared is going to be equal to 0 squared times 0.1 plus 1 squared times 0.2 plus 2 squared times 0.25 plus 3 squared times 0.45. So I'm still going to draw that little line just so I can go ahead and calculate. So I'll get 0 plus 0.2 plus 1 plus 9 times that, 405, 4.05. So I'll get 5.25. So now if I want the variance of x, it's going to be, oops. Okay, so now if I want the variance of x, it's going to be that expected value of x squared we just calculated minus expected value of x squared. So 5.25 minus our expected value of x is 205. So 2.05 squared. So I end up getting something like 1.0475. So this, remember, x is in number of books sold. So, I mean, you could say books if you wanted units. But remember, we want to find the variance or the standard deviation for revenue. So we're not quite done yet. So this is my first step. My second step would be to find the variance of w. So variance of 12x minus 10. The minus 10 part goes away. It doesn't vary at all. So I'm going to get 12 squared times the variance of x. So I'm going to have 144 times that 1.0475 I just calculated. And get 150.84. If you're looking at units, it's dollars squared, which is part of why we tend to not talk about variance as much around people. We are going to go ahead and square root. So my standard deviation for W is going to be to square root the variance for W. So square root that 150.84. And we are going to get something like 12.28169, and it's in dollars. So things to note in general, when we talk about dollars, unless you work for a gas station, you tend not to go past this second place. So make sure you do round appropriately. So looking at the next one, it's a 1, so it's not going to round up. I'm going to say, okay, well, that's about $12.28. So if they have 3 books to sell, and these are the probabilities that they'll sell each number, so the probability they'll sell 0 versus 1 versus all 3. On average, we expect their revenue to vary on average about $12.28. So that's what we're looking at. So that will be our linear combinations example. Definitely work this out on your own. I strongly recommend going through the your turn examples at the end of the slides. They are along with the R examples. Definitely good practice, and we'll see you for lesson 6.